Surgeons need to accurately judge distances and positions during delicate procedures, which relies on depth perception. When viewing the surgical field through a microscope, the image can appear flat, making it hard to perceive depth. By adding a second viewpoint, similar to how our two eyes work together, we can restore that 3D perspective and help surgeons see the anatomy more clearly. Traditionally, surgeons have relied on stereo microscopes for depth perception. These systems split light from the surgical area into two separate views, one for each eye, creating a 3D effect. Today, modern microscopes use digital sensors to capture these views, allowing surgeons to see the surgical field either through classic eyepieces or on a digital 3D display with special glasses. Stereoscopes give surgeons a strong sense of depth or qualitative depth perception. But when it comes to actually measuring precise distances and shapes, or quantitative depth information, it's very challenging to get accurate and complete results from the just two unique camera views these scopes provide. This makes it challenging to bring advanced automation or robotics into the operating room, and it means we can't provide surgeons with precise, real-time feedback when they're using handheld tools. This work presents the Fourier Light Field Multi-View Stereoscope, or FilmScope, our solution to modernize surgical depth perception. Instead of relying on just two camera views, this system packs 48 microcameras into a compact space. Each microcamera has its own high-resolution sensor and a custom lens, all working together behind a high-performance primary lens that gathers light from many angles at once. In a single snapshot, this system captures high-resolution images of the surgical area from 48 unique perspectives simultaneously. Then, as the surgeon works, the FilmScope can stream images at up to 120 frames per second. Finally, we can take a single snapshot from the system and feed it through a custom-designed 3D reconstruction algorithm to transform the multi-perspective images into a detailed depth map. This can then be displayed to the surgeon as an interactive 3D model. Our tests show that the FilmScope successfully reconstructs depth maps across a 1 centimeter range with precision down to 10 micrometers. In the future, the FilmScope can be applied for applications including tool tracking, as well as monitoring changes and deformation in soft tissue. The data produced by the FilmScope can provide surgeons with a unique level of insight and control.